we do experiments with this, with gases. A lot of the times to collect gases, you can either collect them in their own separate vessel, like a container, or you can collect them over water. And commonly we collect them over water because we can easily like submerge something where a reaction's happening, like in a smaller container. Let's see, a couple of years from my class, we did the butane, molar mass of butane. We took a lighter with no flint. We let it open. The butane came out of the lighter underwater. You can collect it. So it's fairly simple. I'll kind of draw out the setup here, though. Essentially, you have a beaker. You have a graduated cylinder. Little graduations on it. And you can have a reaction happen down here. Reaction. And then originally the water might be all the way to the top in the graduated cylinder because like you've got it full of water and you invert it upside down so it's still full of water. But when the reaction happens and gas bubbles form, gas bubbles travel up to the top, and what starts to gather at the top? If gas bubbles are being inserted into the cylinder. Gas, right? So you're going to end up with this big void where there's only gas present. And so that's how you collect gas. You collect it underneath something with water, and it displaces the water from a particular, in this case it's a graduate cylinder. We're going to use things that I told you yesterday. Eudiometer. Eudiometers are glass tubes that look just like graduate cylinders, they're just fancier. So that's how we collect water generally. A couple things that we have to note is the fact that if something is gathered over water, water vapor is always happening. So in my water bottle here, there's little droplets of water on the inside. That's because this water is evaporating and there's little drops of condensation on the inside. So I can actually visualize that. Sometimes you can't see the water vapor, but you know it's there. Where would there be more water vapor? In a hot like setting or a cold setting? Hot, because the water vapor is a gas and it evaporates up and it gets excited and runs around in the air. So we have to know the temperature at which we are collecting our information, our data, because the water vapor pressure, noted as water vapor pressure, that's how you note it, is specific at a specific temperature. It's temperature dependent. Okay, so kind of just do the first part so far. This value for water vapor pressure is not something you would have to know. It's not something you would calculate. No, it is in a book. That book is in the back of my room. I don't have it out right now, but it's very, very specific. So it's something that they've already established, and you look it up in a book. Oh, this thing's blinking. All right. So, well, I can't move up right now. Give me a second. So what we have to do is when we are gathering gases in a situation like our little beaker in our graduate cylinder, you have to look and compare the three different things. The amount of gas present, which changes the water column. So the water column is this amount of water that's left in here. And you have to compare the outside gas pressure. So that's what we have this we have this formula that we implement to determine the gas pressure of that gas that's collected at the top. Because sometimes you can't do it just by measurements. You have to calculate it based on all these other little measurements you know. So a lot of the times we know the P total. We know atmospheric pressure. The Weather Channel gives us the pressure of the atmosphere every day. So all we do is look it up. So like the pressure in here is going to be really close to 1 atmosphere because we're really close to sea level. You minus away the pressure of the water vapor, because in this lovely drawing I have, the water vapor at the very top of the column here, it's evaporating off, and it's actually creating more pressure than what the gas itself is. Does that make sense while we're minusing away the water vapor? Because we need to eliminate only to just the gas we're talking about. Then you have to minus away the water column. And that's the reason why you do that is because this pressure of the atmosphere is actually pushing, this beaker is full of water, okay? Just pretend I can't draw the red there, but it's there. The pressure of the atmosphere is pushing on the water in the beaker. The beaker water is pushing up into the column of water that's in the graduate cylinder. So it's actually that water column itself is causing some pressure, and we have to get rid of that as well, so we have to minus that. But this water column is made of water. Normally you would measure in millimeters. If it were mercury, you could measure in millimeters and say, oh, this is 78 millimeters of mercury. That's how much pressure it's causing. But since we aren't using mercury, we can't just straight up measure the height of it and determine the pressure. We have to convert from millimeters of water to millimeters of mercury using density. And that's where this stuff right here comes in. So if you haven't written this little bit right here down, write that down. So the water column is going to be the height of water times the density of water. Well, let's say it's, I don't know, let's go 70, I'm just going to make up one, 20 millimeters of water. What's the density of water? Generally, it's 1 gram per milliliter. Sometimes it's a little different because it's based on the temperature specifically, but it's 1 gram per milliliter. Well, a milliliter is equal to how many centimeters? Or what in terms of centimeters? Yeah, so the cubic centimeter. I don't have a, there we go, eraser. So that's technically a cubic centimeter. Okay, well that's a cubic, or centimeters cubed. This I could convert to centimeters, yes? How many centimeters? 2, thank you. Oops, that still says 20. Okay, so now the units are starting to look more alike. I'm not going to go through the whole thing right now. But in order for us to convert to the height in mercury, we have to plug in our information that we measure with water, the density of water, and then you can see right here, I've divided by the density of mercury. The density of mercury is 13.6 grams per milliliter. It is so dense. That's what we talked about yesterday. That's why commonly millimeters of mercury is a common unit for pressure. You determine what the measurement of height of water is. Truly, the densities, the density units, density of water, and the density of mercury, they cancel each other out, so you don't really have to change anything because they cancel themselves out anyway, so don't worry your little head over that. Just know that you can get the height from this, the height of mercury. Take that height in millimeters of mercury, and then you can plug it into your formula right here. Whew. That's all just from an experiment, because you cannot determine the pressure of a gas unless you know all this information, because we have some gas pressure gauges, but you can't plug it in underwater. Okay, so plug it in. We're good. Good? All right, do that for this question. A sample of oxygen is collected over water. When you see that over water, you have to be able to look up the water vapor pressure for that setting. Well, the setting is at what temperature? 20. I have that value for you because I had to look at that myself. Okay, so the sample of oxygen is collected over water at 20 degrees and a pressure of 738 millimeters of mercury. So what is this representing? Total pressure of the atmosphere. Good. PT, P total. The volume is 310 milliliters. What is the partial pressure of the oxygen? So question, what is the partial pressure of the oxygen? And then what would be the volume, the separate question, what would be the volume when it's dry? So the volume of the oxygen when it's dry. Dry means minus water vapor pressure at STP. Well, what's STP? 1 atmosphere and 273 Kelvin. So we actually have 2 questions here. We're going to solve the partial pressure one and then solve the volume one. Alright, it doesn't tell us anything about a column of water. So we're going to ignore the fact that there's a column of water because it doesn't give us any information, no height, no nothing. Okay, so how do you get the partial pressure from the total pressure? If you knew the mole fraction. There's a value I said I would have to tell you from the book. This partial pressure of water vapor that's from the book is 720. That's a 2. 720. No, I'm sorry. I'm looking at the wrong value. 17.5 millimeters of mercury. It's generally a pretty low value. So that little bit of water that's in there at this temperature is able to cause that much pressure. Alright, so the total is made up of 2 things. Partial pressure of oxygen plus partial pressure of water vapor. So what's the partial pressure of oxygen, or how would you do that? Right, so 738 millimeters of mercury minus 17.5 millimeters of mercury. That's the value I was trying to tell you. 720.5 millimeters of mercury. and that's the partial pressure of oxygen. It's just a subtraction problem. It's just if you were given information about the height of a water column, you'd have to subtract that as well. Good with the first one. Talk to the people.
Good.
Yes? Okay. I cannot read your minds. I don't actually think I'd want to. Okay. If I want the volume now, and I know the pressure of my gas, so currently my knowns are pressure of oxygen at this temperature is 720.5 millimeters of mercury. What else do I know?
Your
Current temperature is what? 20, I'm sorry, yeah, I just took it away. So 20 degrees Celsius, 0.0, okay? So that's how much in Kelvin? 293 Kelvin. All right, so this is essentially what kind of problem? I've got pressure 1, I've got temperature 1. I'm looking for, thank you, I'm looking for, and here's pressure 2, here's temperature 2, and I have V1, where's that? Oh, 310, right there. There's V1, and I'm looking for V2. What's the law I'm using?
combined gas.
Combined, thank you. So P1, V1 over T1 is equal to P2, V2 over T2. What am I solving for? V2, solve for V2, give me variables first. Cross multiply and divide, that's what I'm asking. P1, V1, T2
over T1, P2.
and P2. Thank you. So all you did was took these, cross multiplied, put them on as 1, and then divided by, I'm sorry, brought the P2 down here. So you're isolating V2 by itself. So when you plug in, all your variable units should be exactly the same. Notice that we've got millimeters of mercury for pressure 1, atmospheres for pressure 2. Well, what's the easiest way to convert here?
1 atmosphere is 7.
Right, 760. Now I'm not going to convert to atmospheres with this one. I'm just going to go straight to millimeters of mercury with the others. So pressure 1. Let me move this so I have more space to write. Oh, okay. Well, this microphone's picking up all my little weird sounds I'm making right now. Okay, well, we'll do this. Okay, whatever. So P1 is 760 millimeters mercury. V1 is 310.
P1 is the 720.
Oh, I'm sorry. Thank you. I saw that one right there, and I've messed up my 720.5 millimeters mercury. This one was 310, right? Milliliters. And then T2 is the second temperature given at Kelvin, or at standard. T1 is 293 that was originally given, and P2 is an atmosphere, so 760. Okay, so therefore you could solve for temperature that way. I did not do a combined gas law yesterday, so I want to make sure everything's good. Just actually including the partial pressure stuff too. Give me a thumbs up when you're good here. Yeah. Okay. This is a lot of chicken scratch right now, but if you, I still do this, and I teach AP chemistry. Okay. I still write down my knowns. I label my knowns, label them 1s and 2s, whatever. Because if not, it becomes it can be a disaster if you don't know what your variables are, because if you know what your variables are, it's really easy to figure out the formula you should be using. I've done this since, I was your age. I feel like it's helpful, and so I write it down every time. Even if I can literally go back and read the question, I still write it down. Yeah. You can go to liters. There's no method to the madness here, unless it's just all the units have to be the same for each individual variable. Okay. All right, I'm going to skip this one for a second. Let's do some stoichiometry. This one. Check back the book for your answers to your questions, but I will talk about homework at the end. Let's do some stoichiometry, and then I'll do a couple questions so that you guys can move on to your simulation. Alright, so we know how to solve basic law questions like Boyle's law or Charles's law or ideal gas law, but so far we've not been using any DCEs, right? We just read the question, we write down the givens, calculate, we're done. So this just adds in another component, stoichiometry, where you have to have a BCE. You have to be able to use mole ratios. But then the question comes, well, where do you get your moles or mole ratios from? Well, mole ratios are definitely going to be coming from the BCE. But the moles, we have the power to calculate. Because we're super smart. We know that ideal gas law. Most of the time you'd be asked to probably write down, most of the time you'd probably be asked to do stoichiometry. So I'm going to show you guys a couple of tricks. You can write, I did print some of this, but it's really small, so it's just there for reference. Okay, so if you have a balanced chemical equation, you can get mole ratios. But sometimes you have to find the original mole to start with. Well, how would you do that? You solve for moles using the PV equals nRT. That's usually generally the first step of solving any kind of gas stoichiometry problem. And then commonly you'll also be given volume, maybe to start with instead of information about moles. So if I was going to give you, like, okay, I've got 2 liters of hydrogen and 1 liter of oxygen, how much water can I make? How many liters of water can I make? Due to the fact that moles and volume are directly related or directly correlated, because as volume goes up, what generally happens, or well, definitely according to this mathematical formula, as volume goes up, what should happen to moles? They also should go up because it's on the numerator. So what we're doing is we're making a simplification of this instead of all the time going to moles. If you're given lots and lots of volumes, we can call them volume ratios. Because if volume is directly related to moles, what I'm going to do is I'm going to go, okay, take my volumes, go to moles, mole ratio, and then go back to volume. When in the end, that middle step can be eliminated due to the fact that they are directly correlated. But they're only directly correlated at the same temperature. So if you're changing temperatures during the problem or during the experiment, you can't do volume ratios because the volumes technically could change based on the temperature and not the moles. So it's only when it's at a constant temperature. So volume ratios of gases at the same temperature and pressure truly too, but temperature is really the big one here. You good there? All right, so let's do a problem. We have 5.6 liters of hydrogen reacting with 1.7 liters of oxygen. What is the volume of water vapor formed? Okay, do not use mole ratios. Use liter or volume ratios because it cuts out about 3 steps. Okay, when you see that you have 2 reactants given to you and 2 data points, what do you automatically realize? What kind of problem is this? LR problem, thank you, limiting reagent problem. That's because you don't know, is hydrogen controlling the product output, or is oxygen creating or controlling the product output? If you don't know who to start with, you can't solve the problem appropriately. Okay, so we're going to set up a before, during, and after table. Okay, it's called a modified odds table. Don't worry about it. It's called before, during, and after for us right now. You're starting off with your BCE. That's your first step. Got it? Second step, before for the hydrogen was 5.6 liters and oxygen was 1.7 liters. Who's my LR?
Oxygen.
Why oxygen?
Still less than 5.
Alright, so you divide by coefficients and it's still less than that one. Okay, so 1.7 divided by 1 is 1.7, 5.6 divided by 2 is 2.8, 2.8, so I'm not writing these values down because I don't want to mess you up. But we know that this is the LR, therefore this is the excess, so oxygen is controlling our product. So minus all of oxygen, minus oxygen in a what ratio? 2 to 1. Add oxygen in a 2 to 1 ratio as well. Really, I only care about this product over here, so how much water vapor is made? 3.4 liters. Okay, so you easily could have wasted about 5 minutes of your precious chemistry time going, okay, well, I gotta get to moles. Well, let me do PV equals nRT. And plug, right. But instead, you just went, I know that I can do liter ratios because it does not indicate anywhere in this problem that the temperature or pressure is changing. Okay? Tricks to the trade, people. Know it, because that would take you a long time to do that for every reactant, and then, go through and do the problem again, and then convert to liters at the end from moles. You get my point? Okay. All right, whenever you have, let's see here, and you do not have to write this part down, this is on your paper. I just want to note that we all know how to do the stoichiometry. If you have STP problems, you know that you can use that special conversion factor of 22.4 liters per mole of gas. That is the only time you are allowed to use that 22.4 liters is when the situation is 1, involving gases, and 2, it's at STP, standard temperature and pressure. So, for example, I'm taking X plus A yields, I don't know, B plus Y, I'm just making up stuff. But if I have a reaction already on my BCE for, I can be giving you grams. You can take from grams of X to moles of X with molar mass, yes? Mm-hmm. And then moles to moles with what? BCE, mole ratios. But then you want to get from moles of your gas to liters of your gas. Do not go through and do P equals nRT. Go straight to using your 22.4 liters per mole. Okay? Only an STP. Non-STP, you have no choice. You have to use the ideal gas law. So if I'm starting you off with the same BC at the top, and I'm giving you grams, and I want you to eventually get to volume of something else, start off the same way, grams to moles with molar mass, your BCE mole ratio to get from moles of something to moles of something else. But here, when you get to moles, that means you have N. So then you have to plug it into PV and RT to solve for volume. And that's just the only weird step we have now that we have gases involved. Last ones, really similar situations, except we're going backwards, going from volume to mass. It's the opposite. So how would I get from at STP, how would I get from liters to moles? Thank you. I would do 1 mole over 22.4 liters, yes? Because liters have to be canceled in the bottom. And then same thing, mole ratios, and then molar mass. And then the last one is if I'm starting you off with moles instead, if I'm starting you off with liters, so gas, that's what you're starting with, you're given. To get to moles, you have to go to PV equals nRT first, then you can do your mole ratio, and then you can do molar mass to get to grams. Those are generally the 4 types of problems you have here. I went through that fast. It's because I understand you know stoichiometry. Any questions on this? I see your faces, and I can't figure out. Yeah. I'll post this online. The video's going right now, too, if you want to watch later. And all that free time. Okay, free time. What is that? Okay, let's do a problem. Ready? BC. Let's do a problem together. You are so prepared. You're overly prepared. Am I really? Yes. A sample of solid potassium chlorate was heated in a test tube and decomposed by the following reaction, which we totally know, Miss Kinley. Tell me.
KCO.
Okay, what? KClO3.
KCl.
Balance.
3 there. 2, a 2, and a 2.
Okay, 2, 2, 3, yes? Okay. Now I'm going to write down, and you see my star here, required on all problems, quiz tests, whatever. Show me your givens. I know it's going to be an extra step, but do it, because you will thank me in the end, because you know how to solve problems. You know how to problem solve, and that's my goal for you, okay? Life problems or chemistry problems, either way. I got you. Okay, so we have to write down our givens. The oxygen produced, it says oxygen, you should have known oxygen is produced, was collected by the displacement of water. What does that ring in your brain?
Over water.
Over water, so that means we have to know what? Water vapor pressure at whatever this temperature is. Let's see if it's on here.
22.
Is it on here?
It's 22.
Oh, I'm sorry, temperature up here. Okay. At 22 degrees C, a total pressure was found to be 754 torr. Good? I'm reading the problem. shaking your head.
I've always been confused as to what
Torr is just like millimeters of mercury or atmospheres. It's called Torr because people like to name stuff after themselves. It's Mr. Torr, Dr. Torr, like Dr. Dre, but Dr. Torr. Okay, somebody last year when we did Chem Club outreach, Trey made us call him Dr. Dre because it was like Dr. Trey, but Dr. Dre. He made all like the fourth graders call him that. I was like, I don't know. Whatever. No, they knew. Okay, so there's our total pressure. The volume of gas collected was 0.650 liters. And the water vapor pressure was, they told us, 21 torr. So that's helpful. We don't have to look up in a book. Calculate the partial pressure. So question, vapor pressure, partial pressure of oxygen in the gas collected, and the mass of potassium chlorate that was decomposed. Alright, so now we have everything we need. I don't have to look at the problem anymore. We have exactly what we need. That is the goal. Because you waste your time reading the problem like 5 times. Alright, so all this is going to be used to find first our partial pressure. How would you first find your partial pressure? Yes, okay. P total is equal to P of gas, which in this case is oxygen, plus P of water vapor. Well, minus away your water vapor on both sides, vape. Then you get P of gas, which is P of oxygen, which is our first question. So total pressure was 754 torr, and your water vapor was 21 torr. All right, what's that in your head? 733 torr. Check. One down. And that's only because we were given total pressure and partial pressure, and you know all this law, like the back of your hand. You got this. All right, how would one find mass of potassium chlorate? Give me a thought process. Okay, you can get moles of oxygen using what formula? Pervner. The PV was on RT. Ideal gas law, what do you even call it? So we can get to moles of that, and then moles. So then how do you get from gas to potassium chlorate? Mole to mole ratio, and then how do you get from moles of potassium chlorate to mass? Right. You're good. You got this. So using your extreme brains, what value do we need here that's not up here for PV equals nRT? We have P. We're looking for N. T is not quite. Give me the real one.
295.
295. Okay. Is this one okay? No, thank you. What do I need to do?
Oh,
Okay, so that's what, like 0.9 something? What is it? Oh, it's like just trusting you, Abby.
sorry, 0.964.
0.964. Oh, I'm looking on 733. I got 0.952.
733 divided by 760. Yeah, divided by 760.
Dude, tell me it again.
0.964.
I believe you and stuff. I went to atmospheres on these first and then converted because I always do that, but it's okay. It's okay. So we got our P, we got our blah blah blah, everything else. So PV equals nRT. N is equal to. Tell me the formula. PV for RT. P is 0.964 atmospheres. V in liters is 0.65 liters. R is 0.0821 atmosphere liters per mole. Okay, I feel like a robot, okay? And then 295. And the grand calculation for our moles of oxygen is what? What'd you guys get?
0.025.
And then she says, oh, that's not even the answer, guys. We're not quite done. What's the last conversion, or 2 conversions we need to do? All right, what was that mole ratio? This is moles of oxygen, by the way.
First to 2.
Um,
3, 3 to 2.
so 3 or 2 over 3, right? So times 2 moles KClO3 over 3 moles of O2. Next one.
4 millimoles.
Okay. 1 mole of potassium chlorate is like, gotcha, 122.55 grams. And that gives us the answer. Oh, thanks, Gabby. She's checking. She's checking after me. Okay, so you should be highly qualified to do this. The only point that I really need to emphasize is, one, units need to be correct according to the law of gas, universal gas law constant there. And then two, if you are calculating moles, or if you're ever doing anything with a PVs and RT, you must be talking about moles of a gas. If you stop here and say, okay, got the moles of potassium chlorate, you're wrong. Okay, this is only for gas. So whatever you're doing, make sure you understand it's for gas. And if you ever have to go to something else, you have to convert out of the gas to the whatever thing you're looking for. Okay? Gas laws are for gases, not for other things. All right, we have right in an hour-ish. I had a lot more, more problems to do with you. I'm going to trust that you guys can practice them, and I can practice more with you. So on here, I've got 1, 2, 5, and then some tutorials that I found online that I'll post online if you guys want some extra help with anything. And yeah. Oh, on the gas, I have to tell you one more thing. On the gas multiple choice, when pull out your packets that says chapter 10 on it, I forgot to fix this typo before I copied. I don't think I fixed it anyway. On question 4, it says something, and I think this is the part that I needed to fix, I think. Read what's it? It's the one that says chapter 10. Multiple choice. It's in the back side of one of your papers. It says that already? Okay. On this, the one number 5, it says there's a balance formula.
It doesn't say N2.
Okay, maybe that's what it was.
Wait, where is it?
It's multiple choice and it says chapter 10 on it. Yeah, it's this one. So fix those couple of problems that were on there. And number 5 said that I gave you balance chemical formula, but I totally didn't. You have to make your own, and you're highly qualified for that too. I just wanted you to annotate that so I wouldn't forget. All right. Here's what I want you to do. Leave your homework on your desk. I want to see your progress. You're going to be doing a simulation in your lab notebook. So your lab notebooks you will need. And I'm going to show you where it is on my website, and you can work together on it. But you both are, or I would suggest only two to a computer. You need to talk about the things that you need to kind of write down. Really pay attention to the qualitative explanations. I think everybody in this class is naturally good at math, so the math and quantitative stuff comes very easy to you. It's the verbalization of qualitative stuff. That's why AP Bio is so much different than AP Chem, because we do a lot of fun problem solving in math, but they have to explain so much more. So you guys need to work on your explanations today. Where do you find this on my website? Oh, there's my class. Well, so yeah, biology. Nice website, AP Chemistry, documents.
It's so cute. I don't know what you're talking about. Miss Emma, we saw those pictures you posted of us on the science website.
Oh yeah.
Embarrassing.
Yes, Mr. McNeil did that actually. I'll blame him.
Oh my God.
Okay, so the one that says gas simulation exercise, what you're doing, when you click on there, you'll see there's a link. That's not it. That's a biology question. I've been having issues with Word. It's been acting a fool. Let me try this one more again. It says a dialog box there. It's because this stupid file won't close.
Why won't it close?